everyone, and welcome to chapter number 5, video number 2, three-phase induction motor dynamic simulation. In this video, we are going to use the Simulink as a platform. For those who didn't watch video number 1, in video number 1 we built M code for the induction machine to cover the steady state analysis and to compare that one with the analytical solution. In this video, we are going to look for the dynamic simulation. We are going to use the same example like what we did in video number 1, but definitely you know that we can change that one to any machine we like, as the M code at the end of the video number 1 was genuine, so you can add any parameters, any constants, and you can run any machine you like. Here we are going to do that one as well. So for the Simulink model, we are going to build that one for this machine. We are going to see how to change that one to be any machine we like. So we have the equivalent circuit, that one at steady state, and these are the parameters. Added to the parameters and constants we had in video number 1, we need to look for the inertia, J, and the viscous friction, because we need that one in the Simulink model. Let me remind you about the results from the M code, or the output from the M code. We have here torque speed characteristics, current speed characteristics, as we can see here. Here at this point specifically, we have what we call it starting torque. And that one is the average starting torque, because in the lab or in the real case, we have some oscillations due to the dynamic performance. And that one is the average value for these oscillations. So what we are going to do using MATLAB Simulink, we are going to simulate the machine as if we are in the lab to record these dynamic oscillations at starting. Look for the current, look for the torque, for the speed versus time. So it's required to simulate the machine and plot the torque, speed, current versus time, and the machine will start unloaded and then loaded after 0.7 second by 69 Newton meter, and that one is a shaft torque. We are going to have a moment of inertia is 0.2 kilogram meter square, and the friction will be 0.045 Newton meter second. Later on in this video, I'm going to show you the effect of the moment of inertia, for example. And here I'm going to explain what is the effect of the friction factor. So this is a model we are going to build, but we didn't understand how do you build this model. I'm going to explain that one in details. So here we have the main plant is the induction motor. And we are going to apply a torque to the machine terminal. That one is a machine shaft. So we are going to apply a load torque 69 Newton meter. When we have the results, we are going to have the developed torque something like 75.9 Newton meter. And the difference between this one and this one, because we have a friction factor. If we put that 1 0, we are going to have this value is pretty close to this one. We have three-phase supply, so we apply the voltage, phase voltage for example, and shift it 120 degrees. We have some measurement devices, current measurements, voltage measurements, and then we can measure the power P and Q. So that one is the input power. Output power, take the rotational loss, so we can calculate the machine efficiency. So we have output power from that one will be torque multiplied by the speed, T multiplied by omega R. So we have here the stator current is 20.5 ampere, the angle of the current, so we can calculate the power factor. So let's look for the results from this one in the graph wise. As we can see here, we have for the first graph, torque time characteristics. At 0.7 second, we are going to load the machine by 69 Newton meter. The machine has a viscous friction at no load 7 Newton meter. If you add that one to 69, you are going to have the final torque, developed torque, something like 75.8 Newton meter. So this is the oscillation I told you about before. So the starting torque is something like this average, or average of these oscillations. So what you are going to see in the lab, that the shaft is going forward, backward until you reach the maximum point, and then you are going to reach to the no load torque. And then once you load the machine at this point, the machine is going to respond to your requirements and give you the torque required. So the developed torque is 75.8. For the shaft, you are going to exclude that one, which is at 7 Newton meter. You are going to have 69 Newton meter in the shaft. Regarding the speed, the machine starts by some oscillations here, as you can see for that one, and then jump to the no-load speed close to the synchronous speed, which is 1500 RPM. Once you load the machine by this torque at 0.7 second, so the machine drops to 1460 RPM. What about the current? The current is going to have a starting current, and the curve or the figure we plotted from the M code is something like that one. So this is what we plot from the M code. So this is the starting current if you look here. So at this point, we have the maximum value for the starting current. So that one could be the current versus speed as we plotted before, but the average for this one or this envelope shows to you against time that the machine starts by a high current or high starting current, and then we are going to reach to the no load current. So no load current is something like 11.9 ampere, and when the machine is loaded, we're going to reach something like 28.45 ampere peak value. RMS value, that one will be something like 20.5 ampere. So this will be the current pattern, and that one will be the speed pattern, and that one will be the torque pattern. So how we are going to plot this curve? This will be our question now. So we need to move to the Simulink platform so to learn how to build the dynamic model and extract the results. So now we can open the MATLAB command window. I'm going to select the proper path. So either you are going to click on the Home tab and then click on Simulink. So that one is opening for you the Simulink, and then open a saved file or a new file as you like. Or you can click here on the file you want, induction motor, for example. So here I open that one for you. So we have here our model. So we are going to run that one, and to save the time, I'm not going to record in this video the simulation time. So I'm going to start now, run. So starting to compile model. So the time starts. I'm going to stop and then run again after the simulation is finished. Now our simulation is finished, and you can see the results here either in a display. So that one will be the speed in RPM, radian per second, power, torque, or we can have graphs or scope for the speed, torque, stator current, and rotor current. Let's look for the speed here. So the speed starts from 0 until reach the steady state close to 1500 RPM. At 0.7 seconds, the speed drops to 1460 due to the loading by 69 Newton meter to the shaft. So that one is the speed, that one is the torque. Let's look for the torque here. So the torque starts by some oscillation. The average of this oscillation is the starting torque, something close to 60 Newton meter. And then we have no load torque or friction torque, and then the machine has developed torque as we can see here. Let's look for the stator current. So the stator current, as I showed it to you before, we have starting by a high current until we reach the no load current, and then the machine is loaded, and this one is 50 Hertz. Let's look for the rotor current. If we look for the rotor current, so we have some oscillation due to the interaction between the stator and rotor at starting, and then we have rotor current something close to 0 because the machine at no load, there is no current in the rotor side. And once the machine is loaded, we have a rotor current by frequency FR, as you can see here, and FR equals SFS. If the speed is 1460 RPM, so the slip is close to 2.5%, so that one is a slip, and the frequency is 50 Hertz, so the frequency of the rotor current is something close to 1.3 Hertz. How we are going to measure that one? You can measure between this point and this point, so 1 over T give you the frequency. Right. So how we are going to plot this graph in the MATLAB, or how to extract this graph outside the MATLAB? So assume we want to have the speed time characteristics, and we are going to take that one to Winword or PowerPoint. So I'm going to click on the speed curve. Here, click on the gear button, and then you're going to find what we call it logging. So once you have that one, you're going to put a name for the variable. So I'm going to choose capital N for the speed, and then you're going to select between those. So I'm going to choose array now. I'm not going in the details for each one. I'm going to choose that one as array. Apply, OK. Once I have that one, I'll turn back to the MATLAB command window. If you are in 2019 version, you can write plot N of all and one. So that one is the time for the speed, or the time curve, or the time axis, if you like to say. N of all and 2, so that one is the y-axis. So that one represents that speed. So let's look here. So we have the speed curve. Again, like what we explained in video number 1, you click on this arrow, you can change the width of this line, you can change the font, you can add grades, legend, whatever you like. Then you can make a copy figure, take that one out from the MATLAB, put it wherever you like. In higher versions, you can click on that one here from the workspace, or you can add the word output, output.n, all in one, output.n, all in two. So let me, for example, here I'm going to plot the torque all in one, torque all in two. So I need to make sure that I use a variable name. So that one is correct. I plotted the torque. Fine. So we can plot the torque speed characteristics. So we're going to use the same function. So I'm going to use that one, but the x-axis will be the speed. Instead of t will be n2. Let's look here. Torque speed characteristics. So that one using the oscillation of the torque until we reach the maximum point. So that one is the maximum torque until we reach the speed 1500 RPM, and that one when the machine is loaded. So if you like to have a torque speed characteristics, so the steady state analysis giving you more clear data. If you like the dynamic performance, torque time and speed time give you more clear results. Also, you can click here for the workspace, for example, N, and that one is going to give you that one as a matrix form. So you can have here the time and speed, and you can take that one, you plot it somewhere else, or you can plot it from here as well. So how to build this model? I'm going to start a new model here, click on new. I'm going to expand that one. Then I'm going to click in library browser. So in library browser, we have Simulink here. So these are the tools we can use. For example, the Simulink stops here for sinks. We have something like display, scope. So if we have sources, we have something like clock, constant, sine wave, whatever. So leave that one now. I'm going to search for what we call it Simscape. So going for electrical. Once you're going for electrical, you're going to search for what we call it specialized power system. I'm going to click on that one. Specialized power system, I'm going for fundamental blocks. So fundamental blocks will be electrical sources, elements, interface elements, machines. I'm going to click on this one. So we have a synchronous machine. MATLAB don't like to use induction motor, or induction machine. They like to use the word asynchronous, because the synchronous machine is running at the synchronous speed. Induction machine is not running at synchronous speed. They like to call it asynchronous machine. So you have here a synchronous machine in per unit or in SI units. I like to choose SI unit. So I'm going to drag and drop that one here. Let me put that one in the middle. As you can see here, we have 3 stator terminals, A, B, C, and that one is 3 rotor terminals. This machine is slip ring, not a squirrel cage. So I want my machine to be a squirrel cage. So let's look for the terminals. That one is the measurements, if we like to take a measurements from this machine, and that one will be the input to the machine. Mechanical input will be the torque. So if we click here, double click, so it tells you that the machine is wound type, so we can make the squirrel cage or double squirrel cage. So if we choose a squirrel cage, and when I click apply, please look for these terminals, what will happen? Apply. So these terminals will now disappear because the rotor of the squirrel cage is not accessible. So let's go for the parameters. You are going to fill these parameters here. So you are going to put the power of the machine, estimated power input, the voltage. So that one is line to line voltage, and frequency. So we are going to put that one something like 415 volt, 50 hertz. We are going to put resistance of the stator in ohms, leakage stator inductance, rotor resistance, and leakage rotor inductance. Those are referred to the stator because, as you see here, the MATLAB put dash. Also, we are going to put the magnetizing inductance, and then we are going to add the inertia and viscous friction and number of pole pairs. If this machine is 4 pole, we are going to put 2. If this machine is 8 pole, we are going to put 4. If this machine is 6 pole, we are going to put here 3. Then we are going to look for the initial conditions, and that one is a mistake usually student didn't notice, that if the slip starts by 0, this means that we are going to look for the machine when the machine reaches the steady state. But if we are going to make slip equals 1, so we are going to start by speed equals 0. So we are going to enter all of these data, apply, okay, fine. So rather than to waste the time for filling the data, I'm going to copy paste my machine. I'm going to open it for you here. So that one, Control C, I put here, Control V, so that one will be my machine. So I'm going to open that one, look inside. So that one is a squirrel cage. I'm not going to use a preset model. So the MATLAB has a lot of preset models. I'm going to build my model by myself. So the mechanical input will be the torque, and they are going to choose a reference frame is the rotor if we're going to use Sparks transformation later on. But now just we simulate this machine. We filled all the parameters. So now we are going to remove this one. We can use our machine. So I need to put input to this torque. So I'm going to the library, going to the Simulink. I'm going to use sources. Then I'm going to use step input. So that one is a step input. Drag and drop. So I'm going to put that one here. So that one just connect between this point and this point. And please notice there is a big difference. I'm going to remove this line again. There's a big difference between something like this torque and something like this terminal. If you see that one square, so that one is a power terminal. But if you see arrow, so that one is a signal. So I'm going to apply that one here. So the signal applied to a signal. And this one at time equal 0.7, for example, I'm going to have initial value 0. The final value will be 69 Newton meter. So that one is apply. Okay. So how we are going to build the three-phase source? There are many ways to build the three-phase source. If you look here for the Simscape electrical, we are going to have that one specialized power system, fundamental blocks, electrical sources. So either you use a AC voltage source, you can drag that one here, or you can use controlled voltage source, or directly you can use a three-phase source. So I'm going to use something like AC voltage source now. So I'm going to drag that one and drop it here. Once I drag that one and drop it here, right click, format. So I'm going to change the foreground color. So that one may be something like red. So that one, I'm going to change that one if you like, format. Background color, and maybe I make it something like green. So whatever you like. So change the color as you wish. If you notice here, that one is a power source because that one is a square, that one is square. So I can connect this point to this point. But I cannot connect this point to this arrow, for example. I'm going to click on that one, double click. I'm going to write the voltage, peak amplitude, peak amplitude. So that one will be phase voltage. So definitely 415 divided by squared over 3. So that one is phase voltage. But I need the peak value, so I'm going to multiply that one by squared of 2. So 415 is a line value. Divide that one by root 3, give you phase value. Multiply that one by root 2 gives you the peak amplitude. Change the frequency to 50 Hertz. And the phase is 0 degrees. Apply. Okay. So I'm going to click on that one, copy paste, Control C, Control V. So that one is here. So if you like to change the foreground color, if you like, so that one is red. I'm going to make that one something yellow. I'm going to connect that one to phase B. But the only difference between this one and the phase A1, that the degrees should be minus 120. And that one is degrees. Okay. So I'm going to copy that one again. Control C, Control V. We have that one for phase C. I'm going to connect that one here. But that one, if you like to change the color, so something like foreground color will be blue. So I use the notation red, yellow, blue if you like. So I'm going to connect the start point of the three-phase source. So I'm going to connect that one by this one and this one to this one. So also we can get a ground if you like. So here we are going to search in the Simscape for that one for fundamental elements. So here we have elements. So maybe in different versions you are going to find the ground in another menu, but here that one under elements, I'm going to drag that one here and connect it to this point. So now we connected the three-phase source to our motor. How we are going to measure these values? So we need to access the measurement point. So if you go here for Simulink, and under the Simulink, you are going to find here what we call it signal routing. So for signal routing, you are going to find what we call it bus selector. So I'm going to drag that one and drop it here. Let me click on that one without connecting anything. So if you click on that one, you are going to find nothing here, only signal 1 and signal 2. Okay, cancel. I'm going to connect the measurement point to this one. Then I'm going to click on that one again. You are going to find here rotor measurements, stator measurements, and mechanical measurements. So I'm going to remove signal 1 and signal 2. Remove, remove. So let's go for mechanical. I need to measure the rotor speed. Select. I need to measure the electromagnetic torque. Select. I need to measure from the stator current phase A. Select. For example, in the rotor, I need to select rotor current phase A, select. So I expect now to find 4 arrows, so apply, okay. So here we have 4 arrows, so we can expand that one if you like. So that one is going to have here a label, rotor speed. Click on that one, I'm going to extend that one here. So we have the option to measure speed, torque. So for that one is the torque. For that one will be stator current and rotor current. So how we are going to see the output? So you have 2 options here. Going to the Simulink Sinks, choose display. So you see that one as a number. So we are going to see that one as a value here. So connect that one. So that one is a signal, connected to a signal. So now you can measure the speed. Control C, Control V. So we can connect the torque here. But someone said that I like to see it as a graph or from 0 speed up to the synchronous speed. So going to the Simulink library, we're going to choose something like scope. So here we are going to put the scope, connect that one here to the speed. So you are going to measure the speed from 0 up to simulation time. I didn't speak about simulation time or setting simulation yet. Fine. So you can measure the current as well, you can measure the rotor current as well. For the stator current, if I measure that one, it's going to give me an instantaneous value. So it's not wise to have display, but I can put a graph or put a scope. But also I need to measure the amplitude and angle or RMS value and angle. So I'm going here to search. If I don't know what that one, I'm going to write here Fourier. So I'm going to find here a block like this one is called Fourier. I'm going to drag that one here and then connect that one to the stator current, as you can see here. I'm going to click on that one. I'm going to change the frequency to 50 Hertz. I'm choosing the harmonic, first harmonic. So that one is going to mirror the magnitude, the peak value of the current and the angle of the current. But I want the RMS. If you like to have it RMS, for example, so you are going here and then going for math. Let's search for math operations. Drag this gain here and then connect that one to this point. And then you are going to have a display connected here, but that one will be 1 over square 2. 1 over square of 2. Because you know that the RMS is the peak over root 2 for sinusoidal wave. So you can measure the peak value, the RMS value now. How to measure the power? So we need to measure the current of the stator, phase A, phase B, phase C. We need to measure the voltage A, B, C. So let me ask a question now. If we run this program now, is it going to work? Unfortunately, no. There's a lot of things we need to do before running this one. The first thing that we need to go to library here, Simscape, specialized power system. I'm going for fundamental blocks. You are going to find here what we call it power graphical user interface. So you need to add that one to your model. So once you add that one to your model, so now that one understands this one is a power system. So that one is not connected to anything. So you need to add it to your model. So now I can run my model? No. Still we need to add any measurement device. So return back to our Simscape library. Specialized power system, control and measurements. We have measurements here and we have another measurements there. So in the newer versions, you can find that one in different places. So you can drag the current measurement. Also, you can drag here and drop voltage measurement. But let me show you here the difference between this side and this side. If you look for the current, from the left side is a square, so power signal. From the right side is a square, signal or power signal. That one is arrow, so that one is a control signal. So if I'm going to use that one here, so I'm going to make a smart idea. So connect that one to this point, and then connect that one to this point. So that one is a short circuit. I click on that one, remove, delete. So now the current is connected in series. Current measurements, the ammeter is connected in series. So if I like to measure or to see the current of the state or phase A from this side as well, I can put a scope here or I can use this Fourier block. The same. So you can put another ammeter here for phase B, another ammeter for phase C. For the voltmeter, I'm going to move that one to this side. So if you look here, we have square, square. So these are power signals and that one is a control signal. So if I measure between this point and this point, that one is going to measure the phase voltage. So if we put a scope here, we're going to measure phase A voltage. So now we can drag from measurements a block like this one. So return back to our block here. We have the ammeters, we have the voltmeters, we have 3 voltages, we have 3 currents. We can apply that one to a block like VABC, IABC to measure the power. So once you have that one, you can get from the math menu, so something like this block. So if you go to the math menu, I'm going to show you that one here. Let's go for math. Can have something like that one. If we drag that one and drop it here, double click, so you can change that one for the number of inputs. So that one is just multiply 2 inputs. But I like to make something like a division block like this one. So that one could be multiply, multiply. You can multiply, divide. So that one is going to give you the chance to divide the input over output. So you got the efficiency. So if you run this model, so that one should work. But actually, no. What we need to do, we need to return back to the modeling. So I'm going to show you that one here. Modeling. Model settings. So you are going to adjust the stop time. So you can adjust that one to 2 or 1.4. It depends on you. So I'm going to choose variable step. So you can choose variable step or fixed step. It's up to you. But if you choose variable step, I recommend to choose ODE 23B step. If you're going to choose fixed step, you can use ODE4, range cutter one, whatever. But you need to adjust the solver details. So here I'm going to return back to variable step. I'm going to choose that one, ODE23P, solver details. So you are going to adjust the maximum and minimum. So that one shows to you the accuracy for your graph. If you put that one very small value, you are going to see the sine wave, for example, something like stepped sine wave. It's not a pure sine wave. So as you increase that one or make that one smaller and smaller, right? So you are going to see fine results, but take more simulation time. So you need to optimize between simulation time and accuracy of your results. So if we return back to the exact model I had here, I'm going to modeling. So I adjust that one to Variable step, ODE to 23 TP, so maximum step size 1e to the power minus 5. So if I change that one to something like 4, so that one is going to make my simulation faster, but I'm going to sacrifice by the accuracy of the model. So I accept that one, I'm going to run it, and this is the results we had before, something like this speed. Let us return back to our model, and then we are going to test the inertia and the effect of changing the inertia on the motor performance. So first thing, I'm going to change the load torque. Rather than to load the machine at 0.7 second, I'm going to put that one 0, so the machine will be unloaded. Then I'm going to change the stop time, which is more than enough to be 1.5 seconds. So let's run our model. So this is the speed. So we have that one steady state roughly at something like 0.4 seconds. So let me plot that one in the MATLAB here in the command window. So we are going to plot the speed. Then I'm going to hold the figure. Back to our model, I'm going to change the inertia from 0.2. I'm going to make that one something like 0.05. Okay. Run. So look for the speed now. So we have oscillations here. So the machine has a lower inertia, so high oscillation. And if we like to look for the torque, look for the torque now that we have little oscillations and the machine has oscillatory response until reach the no load torque. So I'm going to plot this torque, this speed, here. Plot that one here. So we are going to have two figures in the same plot. So can you see that one? So the blue one when we have inertia 0.2 and the red one when we have inertia 0.05. So I'm going to repeat that one. If we have inertia instead of 0.05, we have it 0.5. Apply. Okay. Run. So let's look for the speed. So we can see here that the machine takes a sluggish response but smooth system. So there is no oscillations, but we reach the steady state very late at something like 0.7 second. So here we're going to look for the torque. So if you look for the torque here, you are going to find that one more oscillatory response at the starting until we reach the maximum point, and then we have the no load torque. Also for the current, you are going to find that one takes more time for the current envelope compared to 0.2 inertia. So let's plot that one as well in the MATLAB here. I'm going to plot the speed. Let's look here for the difference between changing the inertia in the three cases. That one is the case when the inertia is 0.2. That one will be 0.5, that one will be 0.05. So now we understand what is the effect of the inertia on the motor performance or dynamic performance. So if we have more inertia, the motor will be more heavy. If you have light inertia, the motor will be in oscillatory response. So before we leave this model, we can change anything, not only the inertia. For example, we can change the supply voltage, supply frequency, and see what is the effect on the motor performance. If we click for the motor here, we are going to click on the parameters. So we can change any values from the stator impedance, rotor impedance, number of poles, inertia, viscous friction. But my advice to you, try to change the rotor resistance. We tested the inertia before, but now try to change the rotor resistance. For example, from 0.32 ohm, make it 1 ohm. And see what is the difference or what is the impact on the motor torque. We did that one before for the M code. When you add rotor resistance or extra rotor resistance, the starting torque increases. But the maximum torque almost still the same, because the slip for maximum torque depends on the rotor resistance, but the maximum torque itself, in some extent, does not depend on the rotor resistance. R rotor over X equivalent give you S maximum torque, while T maximum equal 3V square over 2X equivalent. That one if the stator impedance is neglected. So you are going to test the machine for any parameters you like, enter the parameters you want. But if you don't have a parameter or specific parameters and you want to test the machine performance, return back to the configuration here. You are going to find what we call it preset model. So you can choose any one of those, something like number 1, number 2, or whatever. If you put number 2, for example, we have a motor, 10 horsepower, 460 volt, 60 hertz, and the nominal speed is 1760 RPM. If I return back to my parameters, I find that my parameters are deactivated. So if you like to use these parameters, go back to configuration and reset that one, or put the preset model no. So you are going to find your parameters are active and you can change whatever you like. So now we are going to return back to our slides to conclude this chapter. In this chapter, we explore the process of building a MATLAB code to calculate and plot the key performance of the induction motor. The code is designed to be flexible, so you can consider that one genuine code. You can add or put any parameters, any constant you like, and then you are going to test the motor performance. We looked for the motor, how to build this motor using Simulink model with direct online starting. We didn't use inverter at that time, so we applied a 3-phase source to the motor. So that one gave us a detailed guide how to implement that one step by step. Also, we demonstrated how to plot the motor performance and how to extract the data or the results or the graphs from Simulink and the M code and send it anywhere, something like PowerPoint slides or Winword platform. What will I watch in the next chapter? In the next chapter, we are going to look for the starting techniques and conventional speed control. See you in the next chapter.